Welcome. This week we are starting a new block of the module. We're going to spend a couple of lectures on neural networks and deep learning, and there will also be lab sessions with relevant activities. So today I'm going to start, and the lecture is divided into sections. The first section is about supervised learning, and I'm going to introduce basic models of neural networks and the concept of backpropagation and the backpropagation algorithm, and present some variants of the backpropagation. Then in the second part, we will talk a bit about unsupervised learning. We are actually going to see how the clustering problem is formulated as an unsupervised learning problem and can be solved by special neural networks that have been designed to do clustering. But before starting, we are going to see a video which explains with multimedia what is a neural network and how signals are propagated from the input to the output of a neural network, and what kind of processing is done in the different layers. It presents an architecture which is known as feedforward neural network.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the two videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants, but in these two introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation, And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16? Well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents, or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then, take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number, but for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases. 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra, so for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. Then as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing.
So I hope you found this video useful. There's a link on Moodle to the 3 Blue 1 Brown channel on YouTube. They have some very cool videos about machine learning and also other areas you may find it very useful. This kind of architecture, the feedforward neural network that was presented in the video, it's one of the models that were introduced in the middle of 1980s by Rumelhart and Mark Cleland. And together with Hinton, they introduced multilayer neural networks and derived the concept of backpropagation in a famous paper that started again research on neural networks. These kind of models are now called shallow neural networks to differentiate from the deep networks that have become very popular, like the convolutional neural network, which have tens of layers, of hidden layers. Hinton used the term deep network for the first time in a paper that he had published for the journal Science in 2006, and then again used the term in another paper in 2007. A few years later, we had the collaboration between Stanford and Google, and the term deep learning was used for the first time in a paper that was published in 2012 in the International Conference on Machine Learning. As mentioned in the video, the whole idea of learning is based in this kind of models on learning the weights, adapting the weights, changing weights so that representations are developed inside the network. This representation represents some kind of features, characteristics of the input data. And when it comes to images, on the video, you show that it's possible to extract some kind of segments or patterns from the images that are presented. But in general, it's not so easy to extract these kind of representations and know exactly how the knowledge has been represented inside a neural network. Learning usually is represented by this kind of formula where we have the new weight, it's equal to the old weight plus some kind of correction. Depending on the way we are going to calculate this correction to the weights, different training algorithms can be derived. And one of the most popular approaches is what you see in this slide, which is the negative of the gradient of the error with respect to each of one of the weights. This is a method that is well known in mathematics. It was introduced in the 60s. The first paper was in 1962, actually, as far as I remember, that introduced this concept of minimization with the use of gradient descent. I also mentioned in the video, there are different kinds of activation functions which affect the operation of the nodes. And I have on this slide some of these functions, like the step function is going to make the node operate like a Boolean gate. So the output will be either 0 or 1. Sine function gives you either -1 or +1. The well-known sigmoid logistic activation function, that was mentioned in the video, and the linear activation function, which basically passes the output of the node without any kind of modification or squeezing into some kind of range, like the sigmoid function. And more recently, ReLU, the rectified linear unit activation, has become the most popular because it simplifies the problem of training. It makes it much faster. It's a combination, as you can see. So there is a linear part. So if the input is bigger or equal to 0, you follow the linear activation. Otherwise, for values which are smaller than 0, the output is always 0. Before the multi-layer networks, we had a model which was introduced in the 50s, one of the first attempts to create adaptive networks. This is called the perceptron. And also there is a rule, a special training algorithm for training this kind of perceptron. It was introduced in 1958 by Rosenblatt. And the idea at the time was to create nodes, neurons, to imitate the ways Boolean gates operated. So it was a concept that people tried to investigate at the time in order to produce computers. Okay. The basic idea is this, you can see it on this slide. It's one node, it has two inputs, and these are multiplied with weights. And there is an element which is called linear combiner. The linear combiner can receive also some bias, which is going to affect the size, the magnitude of the signal that goes through the activation function. The activation function in this case, as originally presented, was a hard limiter, which had some threshold. If the threshold is 0, you can see that the output will be 1 if the total input to the function is bigger or equal to 0. Otherwise, it will be 0. If there is a threshold which is different from 0, then you have to change this parameter here. So instead of 0, you have the value of the threshold. And the net input, the total input to the node should be bigger or equal to that threshold. Depending on whether we are going to use a bias or not, the node is going to divide the space into two regions. because it's going to operate like a machine that has only two states, state 1 and state 0, depending on what kind of the value of the threshold that you have. But there is it's always a Boolean case, like with Boolean gates. That was the initial idea. It was in the 50s, and at the time, researchers were trying to design the first electronic computers. So they were experimenting with different approaches, analog electronics, digital electronics, and as part of this kind of work, this kind of model was introduced. So if we have a node with only two inputs, then you can see that the total input is given by this equation. And the output is going to be 0 or 1, depending on the values that these parameters, W's and the X's have. If the node has a bias, then the equation, as you can see, is slightly different. We have an extra term here, which is the bias. And to illustrate how this thing works is, let's assume that we have values which are equal to 1 for the weights and the bias is -1. Then in the first case, the equation becomes x1 equals minus x2 when there is no bias. And if there is a bias, x1 equals minus x2 plus 1. This is for the case when we have a bias. These are basically equations of a linear line. If you go back to geometry that you did in high school, you will see that these are just equations of a line. And this kind of node just divides the space into two regions. This line defines a boundary between these two regions. It's called the decision boundary. Points that are on the line, they're on the decision boundary. So in the first case, the line, this is the first line, when there is no bias, it passes through the origin of the axis, and it divides the space into two regions. In one region, this part of the line on the right side, then it's 1. On the other side, it's 0. Okay, so depending on whether x1 and x2 lie, you can get 1 or 0 at the output. In the second case, the line, as you can see, because there is a bias and the bias is -1, it means that it will cross the horizontal axis at the point +1, and then again it will divide the space into two regions. This region here is where the activation will be 1, and the rest of the space is going to be 0. The perceptron aimed at classifying inputs. These are the points at the input x1, x2, xn into two classes, 1 and 2. And it operated by dividing the space. At the time, the concept of the hyperplane or hyperline, it was introduced, and the perceptron was proved that can solve problems which are linearly separable. These are data sets which can be categorized into two groups, basically, and they can be divided by just drawing linear lines. And I have some examples here, again, graphically, to show you how it works. So you have a two-dimensional space, x1 and x2. These are two features, x1 and x2, which can be used to create different kind of representations for the data, different data points. So you have the line. The line is given by this kind of equation. There is no bias in this case. And the points which are on the line, they're on the decision boundary. And then you have all the x1, x2 pairs that lie on one side of the line. They belong to class A1, and the rest of the points belong to class A2. In the second part, you can see what happens if you have a 3-input perceptron. So you have 3 inputs. Again, there is a threshold. If you have 3 inputs, then we are talking about a plane in a 3-dimensional space in this case. But in general, you can have high-dimensional spaces, so you can have a hyperplane if we are working in a high-dimensional space. The hyperplane is going to, again, divide the space into two regions, data that belong to one region are classified as class 1, and all the other data points will belong to class 2. That's a general idea because the perceptron is able to solve linear separable problems, which is considered one of the limitations of the time, actually. I will explain about that later on. So the perceptron, the whole idea of the perceptron of this simple model is to learn from the data, and this is achieved by making small adjustment to the weights. The weights are in the beginning are initialized, the values are initialized in an interval, say minus 0.5 plus 0.5, and then small modifications are made to make adjustments. The modifications are based on the idea of the error. It's the error between, is defined as the difference between the desired output of this node and the actual output. That's the reason it belongs to this group of methods which are called supervised learning. We assume that someone can give us information about what the desired output of this node would be for each one of the inputs that it receives at each time step. The model assumes that each one of the data points or patterns is presented uh, at each time point and iteratively tries to minimize this error. Intuitively, we can understand that if this error is positive, it means that the perceptron should increase the output to reach the value of desired output. Okay. Rosenblatt introduced the perceptron learning rule, which you see here in this equation. It's the value of the new weight is equal to the previous weight plus some kind of correction. It follows the same kind of principle, but the correction here is defined as a product between a parameter h, the learning rate, it's a positive parameter, smaller than 1 usually, times xi, which is the input. It depends on how many inputs we are going to have. P is the number of data points or patterns that are going to be presented. At E is the value of the error for each one of these patterns. The rule was introduced in 1960 and used to solve some simple problems using this kind of model. It's interesting because, as you will see, the same kind of steps usually are followed today by all the methods that we use to train neural networks. So first step is initialization. Somehow the parameters are initialized. Here are randomly initialized in a particular interval, but in neural networks, different algorithms have also been proposed for initialization of multi-layer networks, but also of deep networks. The second step is the activation of the nodes. In the perceptron, things are simple. There is just one node, and the output can be calculated by using an activation function, which is usually a hard limiter or step activation function. So the output is either going to be 0 or 1. That's how the step function or hard limiter activation function operates. It will receive an input which depends on the products of the inputs times the weight minus the threshold, the value of the threshold that the unit is going to have. So we use this calculation and we activate the nodes. Then there is a step which is about the update of the weights. The update of the weights is based on the errors that are taken into account into some kind of formula in order to calculate how much the weights should change, the amount of weight change. Formula follows the standard rule. The new value is the old value plus some kind of correction. Okay, this delta W is the correction. And as I said, there are different algorithms even today in deep networks, different ways to calculate this kind of correction. With a perceptron, it was a very simple formula. It was calculated by the so-called delta rule because of this delta W that is used. And the calculation was a multiplication between the learning rate, the value X, and the error, which is the difference between the desired output and the actual output. And it's an iterative procedure. You calculate the correction, you present the first input, and the corrections for the weights are calculated, and the weights are updated, and then the network receives the second input. It goes through the same kind of process, and the weights are updated again. At each pattern presentation, the weights are updated. It's a type of online learning algorithm that we use today. And this kind of approach, it usually can learn some basic Boolean functions like the AND function and the OR function, which at the time it was very important to produce in order to fabricate, manufacture electronic computers. Okay, but one of the limitations was that it was not able to solve the exclusive OR problem, for example. Okay, so you couldn't use you couldn't implement hardware that would design hardware that will implement, a perceptron node to make it work as an exclusive OR gate. With AND and OR, things are simple because these are linear separable problems. As you can see, an AND is like a binary classification problem. So when you have 0, 0, the output is 0. So the first three patterns produce 0, which is class 1, let's say. And then there is one pattern which is produce an output of 1, which is class 2. It's similar to a binary classification problem. You have only two classes. The first three patterns belong to class 1. The last one belongs to class 2. By drawing just one line in two-dimensional space, you can see that it's possible to distinguish the patterns, to classify the patterns in two classes. So 1, 1, this data point, it's at the right side of the line, in a sense, so it belongs to class 1, and the other 3 points belong to class 0. With OR, it's exactly the same. We have, again, a two-class problem, class 0, class 1, and the 3 points easily can be classified into the same class by just drawing one line. It's a simple problem that you can solve by drawing one line. And as I said, the lines are calculated by the perceptron, like in this case, for example. So you can design, you can find weights, values for W1, W2, and for the threshold theta, which will allow to draw one line and classify points to implement the AND gate or the OR gate. Unfortunately, this situation is much more difficult when it comes to exclusive OR. It cannot be solved by the perceptron. And exclusive OR is an example of a nonlinear separable problem. We cannot separate the data points by a straight line or a plane or a hyperplane if we are talking about a high dimensional space. Okay, we have to have much more complex models, more complex activation functions, which will allow us to create hypersurfaces that will allow us to classify the points into different classes. And this is how the whole idea of multi-layer neural networks, the reason it was introduced. A multi-layer neural network or multi-layer perceptron, that was the initial original name. It was introduced in the 80s. It's a kind of feedforward neural network which has one or more hidden layers, like the one shown in the video before. We have an input layer, which gets inputs from the environment or from sensors. Then we have layers in the middle. These are called hidden layers. And then we have the output layer. And the signals from the input are propagated from layer to layer. There is always one-way transmission of the signals from the input to the output. And the process is done on a layer-by-layer basis. The networks of this type look like that. That was one of the contributions in the 80s by Rumelhalt and some other researchers, which introduced these kind of models with many hidden layers. Another contribution at the same time was the introduction of the sigmoid activation function. So instead of using hard limiters or step functions, they decided to use sigmoid activations, which allowed them to exploit a number of methods from numerical optimization. optimization algorithms in mathematics. Why it's called hidden layer? The layers in the middle, usually they are called hidden layers. Even in deep networks, we are talking about, the deep layers or a large number of deep hidden layers. They are called hidden layers because they hide their desired output. We don't know exactly what the output will be, which is one of the difficulties. It's not so easy to find the right amount of correction to update the weights of these nodes. I made perhaps a distinction between, I need to make a distinction between networks like multi-layer neural networks with 2, 3, up to 5 hidden layers, and the network which have more than 5 hidden layers, 40 hidden layers, sometimes 30 hidden layers, 40, 100 hidden layers. That we call nowadays deep networks. These original models with few hidden layers, they are called sometimes shallow artificial neural networks. The hidden layers can have 10 to 1,000 neurons. With deep networks, we have now a large number of hidden layers, and we have reached networks which have trillions, 1 trillion of weights, for example, a very large amount of weights to update, which makes obviously training of these kind of models quite complex. Nevertheless, one of the methods which is still used is the backpropagation algorithm. The idea of the backpropagation is it follows the principles of the perceptron, in the sense that you have to initialize, and then you have to calculate the activations of the nodes and use this information to calculate the output and produce an error, and use this kind of information to update the values of the different weights. That's the idea behind the backpropagation algorithm. It belongs to a group of technique which is called supervised learning. Okay, someone, they assume, needs to give you the desired output in order to calculate the error. This kind of idea of supervised learning was introduced in 1962 by Abramson, and I have the reference here, learning to recognize pattern in a random environment. They first, according to my knowledge, these are the first people who introduced this kind of concept, and in a paper that was published in the transaction information theory. That was the Institute of Radio Engineers at the time. Now it's called the Institute of Electronic Engineers. And they still publish the IEEE transaction and information theory. So one of the first one of the volumes in 1962, they introduced this kind of concept of supervised learning. In the backpropagation, this idea of supervised learning has two phases. The first phase is to use the data, propagate signals through the different layers, and generate the output at the output layer. If the outputs are different from the desired outputs, then calculate the error and then propagate the error backwards into the different layers, starting from the output and then going into the hidden layer, which is close to the output. And you go backwards and you update, you modify the weights. So you have two passes. One pass, it's called the forward pass, where the input signals travel from the input through the layers and go to the output. And then the calculation of the error and the error signals are transferred backwards. They are transmitted backwards, and they update the different weights of the network. I have a very nice video which explains how this process works in a multi-layer neural network, and I think I'm going to use it now to easily explain how this approach works.
The hard assumption here is that you've watched part 3, giving an intuitive walkthrough of the backpropagation algorithm. Here, we get a little bit more formal and dive into the relevant calculus. It's normal for this to be at least a little confusing, so the mantra to regularly pause and ponder certainly applies as much here as anywhere else. Our main goal is to show how people in machine learning commonly think about the chain rule from calculus in the context of networks, which has kind of a different feel from how most introductory calculus courses approach the subject. For those of you uncomfortable with the relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is AL-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function like the sigmoid or a ReLU. It's actually going to make things easier for us if we give a special name to this weighted sum, like Z, with the same superscript as the relevant activations. So this is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute Z, which in turn lets us compute A, which finally, along with a constant y, lets us compute the cost. And of course, AL-1 is influenced by its own weight and bias and such. But we're not going to focus on that right now. Now all of these are just numbers, right? And it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these 3 ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's kind of a lot of symbols, and take a moment to just make sure it's clear what they all are. Because now we're going to compute the relevant derivatives. The derivative of C with respect to AL works out to be 2 times AL minus y. Notice, this means that its size is proportional to the difference between the network's output and the thing that we want it to be. So if that output was very different, even slight changes stand to have a big impact on the final cost function. The derivative of AL with respect to ZL is just the derivative of our sigmoid function, or whatever nonlinearity you choose to use. And the derivative of ZL with respect to WL, in this case, comes out just to be AL minus 1. Now I don't know about you, but I think it's easy to get stuck head down in the formulas without taking a moment to sit back and remind yourself of what they all actually mean. In the case of this last derivative, the amount that small nudge to the weight influenced the last layer depends on how strong the previous neuron is. Remember, this is where that neurons that fire together wire together idea comes in. And all of this is the derivative with respect to WL only of the cost for a specific single training example. Since the full cost function involves averaging together all those costs across many different training examples, its derivative requires averaging this expression that we found over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del z del w term for a del z del b. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of z to the previous activation, comes out to be the weight, WL. And again, even though we're not going to be able to directly influence that previous layer activation, it's helpful to keep track of, because now we can just keep iterating this same chain rule idea backwards to see how sensitive the cost function is to previous weights and previous biases. And you might think that this is an overly simple example, since all layers just have one neuron, and that things are going to get exponentially more complicated for a real network. But honestly, not that much changes when we give the layers multiple neurons. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being AL, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter K to index the layer L-1 and J to index the layer L. For the cost, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output. That is, you take a sum over ALJ minus YJ squared. Since there's a lot more weights, each one has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight matrix that I talked about in the part 1 video. Just as before, it's still nice to give a name to the relevant weighted sum, like z, so that the activation of the last layer is just your special function, like the sigmoid, applied to z. You can kind of see what I mean, right? Where all of these are essentially the same equations that we had before in the one neuron per layer case, it's just that it looks a little more complicated. And indeed, the chain rule derivative expression describing how sensitive the cost is to a specific weight looks essentially the same. I'll leave it to you to pause and think about each of those terms if you want. What does change here, though, is the derivative of the cost with respect to one of the activations in the layer L-1. In this case, the difference is that the neuron influences the cost function through multiple different paths. That is, on the one hand, it influences AL0, which plays a role in the cost function, but it also has an influence on AL1, which also plays a role in the cost function, and you have to add those up. And that, well, that's pretty much it. Once you know how sensitive the cost function is to the activations in this second to last layer, you can just repeat the process for all the weights and biases feeding into that layer. So pat yourself on the back. If all of this makes sense, you have now looked deep into the heart of backpropagation, the workhorse behind how neural networks learn. These chain rule expressions give you the derivatives that determine each component in the gradient that helps minimize the cost of the network by repeatedly stepping downhill. If you sit back and think about all that, this is a lot of layers of complexity to wrap your mind around. So don't worry if it takes time for your mind to digest it all.
I hope the video helped you to clarify how this backpropagation algorithm works. One thing that the backpropagation is trying to do is to minimize the error of the network. This is because the whole problem of training has been formulated as an optimization problem. It's actually a minimization problem, minimization of the error. So what we are trying to do is to minimize the error of the network with respect to these weights and the data that the network receives. As I said, the basic idea is that you have the weights, the new weights are equal to the old weights plus some kind of correction. And A popular way to calculate the correction is to multiply the learning rate or step size, it's called in optimization theory, with the search direction. The search direction is a vector which depends on how each algorithm calculates it. Okay, so there are different ways to calculate the search direction. It's the way, it's the direction towards which the algorithm will update the weights. And you saw the video, the gradient vector, which calculates the derivative of the error with respect to each one of the weights. In optimization theory, a gradient vector exists for any differentiable function, f capital, in this figure. If the function f depends on parameters x1, x2, xn, then we can calculate the partial derivative of the function with respect to each one of these parameters, and the result produces the gradient vector or Jacobian of that function. The optimality condition states that when at the point where the derivative is equal to 0, then we have a minimum. But the problem in general in optimization is that this definition of the derivative, it's not enough to guarantee that you're going to find the global minimum. The global minimum is the point of where the function gets the minimum value. Sometimes in optimization, we stack, the algorithm stack into local minima, like in this case, a local minimum. At a local minimum, the derivative is also 0, but the error is higher. The value of the error or the value of the function is higher than the value at the point of the global minimizer. Okay, and in neural networks, there has been a lot of discussion about how we can avoid local minima, and there have been different approaches for avoiding local minima. The backpropagation calculates the derivatives and uses the method of the steepest descent. Steepest descent, it's a type of gradient descent algorithm where the next value of the parameter x is selected if it reduces the value of the function. So you have that the value of function f at the point x k plus 1, that's the next point, the updated one, should be smaller than the value of the function at the previous point. And according to the steepest descent, because one could produce different types of gradient descent algorithms, according to the steepest descent, one way to quickly maximize the decrease of the error is to follow the negative of the gradient. So the steepest descent algorithm says that the parameter at the next step equals the value of the parameter at the current step minus a, which is the step size, times the gradient at that point. Okay, so it's in neural networks and in machine learning in general, we use the term learning rate for the step size, and the x's are the values, the parameters of the model that we want to learn. Like in a neural network, these are the weights, for example, and the biases of the neural network. The gradient will be calculated by backpropagation. Which, as mentioned in the video, it's an application, a generalization of the chain rule for calculating derivatives. We learned the chain rule for calculate derivatives in high school. I have a simple example here to show you how this steepest descent operates for a function of this form. Usually we have a starting point, that's the x0, and you can see the values of the starting point, and this is the value of the step size. So this is the vector of the derivatives. These are the derivatives of this function with respect to x1 and the derivative of the function with respect to x2. So we follow the rules for calculating derivatives. The function, if we calculate the derivative of this function with respect to x1, we are going to get this term. If we calculate the derivative of the function with respect to x2, we are going to calculate the result is this function. And if we use the values for x1 0.5 and for x2 0.5, then we assign the values here, then we can calculate the gradient vector. And you can see that the gradient in this case for these points, it has the value 3 and 3. Following the steepest descent, we can use this information to calculate how much the parameter x the vector of the parameters is going to change. So that's the new value, which is the old value. The old value is the initial value minus the step size and the gradient vector we just calculated. So we put the values here and we calculate that the new value for x1 will be 0.2, 0.2. So as you can see, the values decrease. We moved from 0.5, 0.5 into 0.2, 0.2. That's the new value of the vector x. In the next iteration, what we are going to do is that we are going to use these values as starting points. So these are now the values minus a. A is again the step size 0.1, and we have calculated the vector of the derivatives, which is in this case 1.8 and 1.2. This is the gradient calculated. This is the derivatives calculated at this point. So if you put in these equations 0.2 and 0.2 and you calculate the gradient vector again. So you can put the gradient vector here and then you can calculate the result, which is the new value for the x's. The new value of the vector is shown on the slide. And you do several iterations until you reach a point where these values do not change very much, which means that you have reached a minimizer of the function. If we try to use this kind of idea in the context of neural networks, then I have a simple example here, a nonlinear neuron. So we have a node which just receives two inputs. The inputs are multiplied with weights, and the activation function has a sigmoid shape. And someone gives you the desired output, and you calculate the error. So this is the input vector. So these are values for x1 and x2. These are pairs of -6, 1, -6.1 and 1, etc. And these are the desired outputs for each one of these inputs. And what I've tried to do here with using the sigmoid activation function is to produce a visualization of the error surface. These are all possible errors that can be produced for these inputs and these desired outputs in the intervals -3, +3 for W1 and -5, +5 for W2. Okay. So plain changing with the values of W1 and W2 in this kind of intervals and calculating all the errors is going to give you an error surface like this one. And what we can see here is that there is a global minimum. There are values for the weights. These are actually very close to 0. It's this point here where the error gets the minimum value. But you see what happens. There are also areas where the error is flat, like these areas. So no matter how I'm going to change the weights here, you remain in a flat area where the weights, the error is not going to change much. And there are also valleys. These are here, which lead to local minima, actually. And you can see what kind of shape it has. This is a very simple example, but actually shows you the problems that you encounter when you train with neural networks. There are areas which look always flat until you reach a point, a saddle point, and then there is a change of slope. It becomes negative, and you move towards, a local minimum or a global minimum if you are lucky enough. The role of the learning rate in this context is very important. This is a contour plot of in the neighborhood of a local minimum. The local minimum is at the center here, and you can see the trajectory starting from a point, the different lines and the different, the dots show you the different dates of the parameter values at each time step. And you see how smoothly it goes, it reaches the local. This is achieved with a small value for the step size or learning rate. That's why neural network, most of the time we have very small values, almost close to 0 for the learning rate, so that you have a smooth trajectory. So the weights are updated gradually and they can reach smoothly the right value, so that you don't overshoot the errors, you don't increase the errors. There is always constant decrease of the learning error. The situation changes completely if you use the wrong values for the learning rates. That's why many algorithms nowadays try to update the learning rates automatically by using information from the training process in order to avoid this kind of situation. Still, it's problematic. You have to be careful most of the time. And you can see why here. These are two different values for learning rates, 0.37 and 0.39. And you see now that was previously a very smooth trajectory. It completely changes. There are oscillations which do not allow the algorithm to converge to the value. In the first case, when it's 0.37, actually, after a lot of effort, you see the oscillations, a larger number of iterations, the algorithm will converge. A small increase to the value of the learning rate to 0.39 completely causes a huge problem. This kind of algorithm will diverge. It's not going to be able to converge to a good solution. It oscillates and will fail to learn the data, basically. Okay. In the video you mentioned, the chain rule was mentioned. We learn about the chain rule in high school when we learn basic calculus. And I have an example here. It is used to calculate the derivative of a composite function, like cos n, when n is another function, the exponential function. So you have f is a kind of composite function, and there are rules for calculating derivatives of composite functions, and you can see the calculation on the slide. And in calculus, when we learn calculus in high school, we learn the types of different functions, and there are clear formulas to calculate the derivatives that we learn to use to make quick, simple calculations of functions. In a neural network, the situation, of course, it's much more complicated because we have several nodes and we have several layers. So the calculation of the application of the chain rule to calculate, all these derivatives, it's much more complex and cannot be done by hand. You need to use software to do it. And one of the contributions by Rumelhalt, Hinton, and Williams was the introduction of the backpropagation algorithm in a paper, in a short actually paper that they published in Nature in 1986. It was a 4 pages paper. They trained the proposed algorithm, and they were able to train networks with several, many hidden layers. That was considered one of the major contributions. Training this kind of networks, it was impossible for several years, for decades actually. Rosenblatt, that introduced the perceptron, failed to generalize this kind of architecture and produce networks with many layers, and was one of the reasons that research in neural networks stopped for 2 decades. One of the things that, the contributions that Rumelhalt, Hinton, and Williams did in the 80s was the introduction of the backpropagation algorithm, which was actually, and the introduction of the sigmoid activation function. Using sigmoid activation functions allows you to use errors, which are functions, are differentiable functions. You can calculate derivatives. Calculating derivatives means that you can now use a huge variety of algorithms from optimization to update the weights, the parameters of the neural networks. Okay. The algorithm for backpropagation, as it was proposed by Rumelhalt in that paper, follows the same kind of idea that is used in the perceptron rule, same kind of steps, stages to apply the method. And one of actually of the first names that was used, it was generalized perceptron rule. Instead of backpropagation. Okay, many people used to call it the generalized perceptron rule. The first step is initialization, and as I said, there are different ways to initialize random values in an interval -1 plus 1, or in a smaller interval around 0, 0.1 minus 0.1, 0.1, or people have proposed algorithms, techniques to initialize the weights, like the one I have here, one of the first methods proposed in the 80s for initialization. So you initialize in a small range defined by the total number of the inputs of the neurons in the network. That gives you bounds the interval where the initial weight should be initialized. And then you have the phase of activation, where you pass inputs through the network and you calculate the outputs of the neurons in the hidden layer. And the outputs take into account the activation function, which in this case is sigmoid. In the perceptron, we had the step function or hard limiter function. Here we have the sigmoid activation function. And then you continue, you calculate the outputs at the output layer by using the information from the previous layers. That is the so-called, so far we are doing the forward pass, where information goes from the input to the output. And then we have the phase or when we want to update the weights, and there are equations which help us to update the weights, connecting the hidden layer, the last hidden layer, to the output layer. And there is a different equation that help us to calculate updates for the weights that connect the different hidden layers. So here you see on this slide how we calculate the gradients of the neurons for the output layer. And we calculate the errors, and we use this information to calculate the weight corrections. The weight corrections are used to update the weights, connecting hidden nodes to output nodes. Okay, so this is the formula. The new is the old plus the correction. The correction is given by this kind of equation. This is the learning rate. These are outputs, and this is the delta term, and the delta term is given by this kind of equation. It takes into account the error. We know the error because it's the difference between the desired output and the actual output of the node. And since we are operating in a supervised learning context, we assume that we have some information about the desired outputs. And this is used to calculate the errors. And we have the outputs, and you can calculate the delta term and use it here to calculate the correction, the delta W, which is the correction of the weights, and you update this kind of weights. And then you have to do the same in order to update the weights at the hidden nodes. And you can have several hidden layers. If you have only one, then you apply this kind of equation only once. Otherwise, you continue and you propagate the errors and you calculate updates for the rest of the hidden, for the weights of the other hidden layers. The equations here, as you can see, become slightly more complex. And this is because we take into account the weights, these W's. These are the weights that the weights of the previous, from the previous calculation. So first we have to calculate the weights, the updates for the weights that connect the hidden node to the output node. And once we have these values, we can use them in this kind of equation to update the weights of the previous layers. This is how backpropagation works, and this is a very elegant formulation that was proposed by Rumelhalt in that paper. An elegant calculation which allows to update the weights of multi-layer networks and does not depend on how many hidden layers we are going to have. And then it's an iterative procedure. We have to go back and update again as data are presented at the input of the network. In a more compact formulation, this is how the backpropagation rule works, which is the new weight equals the old weight and the correction. The correction depends on the negative of the gradients, and this is eta is the learning rate. Okay, so this nabla of E is the Jacobian matrix, which is given by this kind of equation. Okay, instead of F is the general term that is used in optimization. Here, the function is the error function. And the problem, of course, in contrast to classical optimization, in optimization, usually you are given the function F. So the function F is available in analytic format. You have a kind of equation. The problem in neural networks training is that we don't have this equation. Okay, we cannot express analytically this kind of equation, this function. Okay, we don't have the function. The function is generated each time that some data are presented at the input of the neural network. We calculate a value of this function. So we use this kind of value, the error value, through the backpropagation algorithm to calculate these kind of derivatives and use them to update the weights. From the 80s, in the same work, Rummelholt proposed a rule which is called backpropagation with momentum. It's given by this equation. It uses an extra term. It's called the momentum term. And the momentum term m is multiplied with the difference of the weights. So you have the old weight, the correction, which is the negative of the gradient, plus an extra term, which takes into account the difference between the values of the weights at k and k minus 1. Okay, and it has been shown that this kind of additional term helps a lot to avoid convergence to local minima, and somehow it speeds up the algorithm and helps the algorithm to escape from neighborhoods which leads to local minima. There have been some other approaches to speed up the training. One of the most popular approaches, you can find it in many packages, is the RPROP, the resilient propagation algorithm. The RPROP is an attempt to adapt the learning rates so it avoids, a poor choice of initial learning rate and the poor choice of initial weight. In a sense, it uses a different learning rate to adapt each weight. It doesn't use the size of the derivative. It just uses the sign of the derivative to determine the direction of the search. And it uses a scheme which compares derivatives. Derivative calculated, the vector of the derivatives calculated at WK, and the derivatives calculated at WK minus 1 on the previous iteration. So it compares these two derivatives and checks whether there is a change in the sign of these derivatives. So if the product of this derivative is positive, then the learning rate is selected by a special formula. If the sign of the product is negative, then there is a different formula to update the learning rates. And if the product is equal to 0, then the learning rate remains the same. It doesn't change. In the first case, we see that the change depends on a factor that aims to increase the value of the learning rate. This is eta plus. In the second case, there's a factor which decreases, in reality, the value of the learning rate. That's eta minus. So the values of the learning rate at each time step, they are increasing or decreasing depending on how the derivative changes. If it has a positive sign or a negative sign, this is going to cause an increase or decrease of the learning rate. This is how the algorithm looks like in pseudocode. So it will check the derivative, the product of the two derivatives. If it is bigger than 0, it will select the learning rate with this kind of formula. There is an upper bound because we don't want the values to increase too much. This formula is going to increase the value of the learning rate, but we don't want it to become extremely large, so you have to set a value for the largest allowed increase. This value can be large, 10, 100, something like that. And then you calculate the correction using this equation. If it is the product is negative, then there is the other formula, and you can you decrease basically the learning rate, and you calculate the correction. And this is what happens if the product is 0. There has been a version which has generalized resilient propagation to deep networks because you cannot use the current formula as it is. You have to update it, and it will help the algorithm to train deep networks. This is another version. You can find it in packages, neural network packages like R, in the neural net package of the R in the R programming language. It's called global alprop or grprop, which uses exactly the same idea for the increase or decrease of the learning rate, but it also uses an extra trick to guarantee that the algorithm will always converge to a desirable solution. It's not going to diverge, no matter whether you make a mistake in setting the hyperparameters like upper bounds or lower bounds for the learning rates, or initial values of the learning rates. This is guaranteed by using these kind of conditions, which restrict the changes in the updates of the values. That was an algorithm that was designed by us here at Birkbeck and has been incorporated in the R neural network package. Although it's not incomplete, it's not fully complete. They forgot to include a couple of steps. Now I'm moving to the second part, which is about unsupervised learning. It's a completely different idea. In supervised learning, we said that we have someone which gives us the desired output. So we can use this kind of information to calculate the errors. In unsupervised learning, you don't have the error. It's the algorithm itself that needs to produce some kind of error and use this kind of information to update the weights. Instead of the error, what we have is the concept of similarity. So the error is based on the concept of similarity in unsupervised learning. And there are, of course, different ways to calculate a similarity. The algorithms calculate similarity between data points presented at the input of the network and values of the weights. That's a very simple way to do it. The first ideas about a supervised learning appeared in this paper by Daly, Adaptive Binary Detectors, Stanford. It was a technical report at Stanford University in 1961. And the whole idea was formalized mathematically in the context of probabilistic Bayesian theory. In this paper, optimal unsupervised learning multi-category dependent hypothesis pattern recognition, which introduced the idea of unsupervised learning for pattern classification based on Bayesian theory. It was published in IEEE Transaction and Information Theory in 1968. Basically, we can use unsupervised learning to solve clustering problems. In a clustering problem, we have a number of data points and we have a number of clusters. So we want to assign n points into m groups, m clusters. And of course, this can be done, but you can see here the number of possible combinations that one could have. You can calculate it using this kind of formula, which is called the Stirling numbers of second kind. And the number combination is huge if you want to try all possible combinations. And I have some examples here. So if you have 15 points and you want maximum, 3 clusters, you have around 2 million combinations to try. If you have 20 points and you have 4 clusters, then you see what happens. These are how many? Around 4 billion combinations. And when you have 100 data points and 5 clusters, then you have 10 to the power of 68. Okay, now in the cluster problems that we want to solve, usually we have thousands of data points, and sometimes we have, I don't know, 10, 15, 30 clusters. It depends on what kind of problem we are trying to solve. Since we are modeling the whole clustering problem as a learning problem, we are again going back into optimization. So we have a function that we want to optimize. So the whole problem becomes an optimization problem again that we can solve by training, finding weights of the neural network. We have a cost function, and we optimize that function, minimizing the error again. But as I said, the error is not based on the difference between the desired output and the actual output, because we don't know what the desired output is going to be. But we update the weights, and that helps us to find clusters that represent this kind of all these kind of data points that we have. Okay. So I have an example here how this can be done. A simple algorithm to do it would be to use as a metric this kind of function. It's the difference between weights and data points. And this will give us also a measure of the quality of the clusters. W star is the center, the cluster centers, as we say in clustering, okay? But the cluster centers correspond to weight vectors that the training algorithm has found as optimal for this group of data points, okay? And the whole problem in terms of unsupervised learning is again modeled as a minimization problem of the error. So the error function is defined by this equation, is the difference between W's, Wi, these are weight vectors, and X, these are data points. So we calculate differences between weight vectors, weights of different nodes, and data points, and we are trying to minimize this kind of error. Minimization of this function will help us to find the optimal cluster centers. The minimization is based, again, if we use a gradient descent approach, then we have to calculate the weight corrections. And the weight corrections are given, the best way using the steepest descent is to get the negative of the gradient. So the weight corrections are the negative of the gradient times epsilon is the learning rate in this case. And we have the partial derivative of the weight of the error. And the weight is the weight of unit j to unit I. If the unit I is the winning node, which means that it has, the weights are the define the cluster center, then the partial derivative is defined by this simple equation. And we can use this kind of idea to derive a class of learning, and supervised learning algorithms are called competitive learning. A competitive network has 2 layers. This is the input layer, and this is the output layer. And you have connections. The connections carry weights, and as you can see, the inputs are multiplied with weights, and one of the output nodes receives input from different receive different inputs. Each one is multiplied with a weight, and each node has its own input vector in a sense. And each one of these nodes node is going to represent one of the cluster centers. The coordinates of the cluster centers are the values of the weights that go into this into this node. If the node, the activation of this node is the largest one, then we say that this node is a winner. There are different schemes. In the graph that I have here, you see that there are connections between the nodes, between the output nodes. So it is possible to have this kind of architecture where each one of the output nodes corresponds to one of the potential clusters, and each one of the nodes, once activated, it tries to deactivate the other nodes. The node that remains active at the end, it's called the winner. Let's see how this competitive learning scheme operates. So the first thing we have is the excitation of the output units. This is done in the normal way. You have inputs which are presented in the network. The inputs trigger input nodes. The activations are multiplied with weights, and then the total of the weighted products goes into the output node. This input, it's called here the net input of the ith node, and it's going to, it's produced by adding the weighted products of the signals that this node receives from the inputs. There is a kind of competition between the output nodes. As I said, there are different ways proposed in the literature to do this kind of thing. One thing is to use, you simply use the max rule. So you calculate the outputs of the nodes and you pick as a winner, the one which has the maximum output. There's another thing which is called the direct competition of the output units in case there are connections between them. So there is a kind of competition where the more active unit tries to deactivate the other units. Okay, and we calculate, for example, like in this case, the output of unit 2 depends on the total input that this unit received minus the activation of unit 1 and the activation minus the activation for unit 3, if we have, like in this case, 3 units. Okay, so to calculate the activation of this kind of unit, of the second unit, in this equation, you have to take into account the total input that this unit receives from the input units, and these are multiplied with the weights, minus the activations that the unit is going to receive from the neighboring units, the unit 1 and the unit 3. And these units normally try to deactivate unit 2. That's why the activations have a minus sign. And then we have the update of the weights, like normally happens. And again, there are different formulations for doing this kind of update. And you can see here 2 ways one could do it. The weights of the connections to the winning unit are updated using this kind of formula. If the unit wins, then you follow this rule and you update, the weights. If the unit loses, then you have to put a 0. Okay, so only the weights of the winners are updated. The other weights do not update. They stay the same. Okay, there are also methods which reduce the weights of the losing units. That's another formulation which takes into account not only the weights and the activations, but also the input data. Okay, different rules proposed in the literature. I have an example here to show you how things work graphically in a 2-dimensional space. Okay, and I'm going back again to the initial formulation of the rule. We said that, look, generally what happens in neural network is that the new weight, the weight at the new iteration is the old weight plus some kind of correction. It's exactly the same idea here. The way the correction is calculated is obviously different from supervised learning. So you have the new weight, the old weight plus the correction, and the correction is given by this kind of equation. It's the difference between the input and the weight vector times the learning rate, which is epsilon, defined by epsilon here. Okay, so that's the learning rate. And this is how things work graphically, assuming that this point shows you the weight vector at time k, and x is the data point that is presented at the network at time k. These are basically two vectors in this two-dimensional space. Okay, I'm using a simple example with 2 dimensions. So x, which is a data point which is presented at the input of the network, is just one point in this two-dimensional space. And the w is again two weights which are also represented by a data point in this dimensional space. So basically we have these two vectors. That's the w vector, and this is the x vector, the vector of the inputs. So what this rule says is that, look, the new weight vector is the old weight vector plus some kind of correction. Okay, what is this correction? This correction is given by the difference of these two vectors. So if I calculate the difference between the vector x and the vector w in this space, is this line. This is the difference between these two vectors. It's denoted by this small vector. Okay, all of it. All right, but because I'm using the learning rate, what the learning rate is currently doing is, because the learning rate has a value which is smaller than 1. Okay, so it's going to reduce the size, the length of this vector. So depending on the value of the learning rate, what I'm going to have is a point somewhere between, along this distance between these two vectors. Okay, so this is the new point that I'm going to use. This is going to be the update. This small vector now is the update. Okay, this is the delta W basically, this small vector, because I multiplied this big one with the learning rate. So I get something smaller depending on the value of the learning rate that I'm using. And then what I need to do is I need to add these two vectors, which is going to give me basically this position, this location for the new weight vector. And that is going to be the new vector WIK plus 1. What these kind of algorithms are doing, because they don't have a desired output, okay? So what they are doing is that they change the weights, not to reduce some kind of error, but to make the weights similar to the inputs that the network receives, okay? So every time the winner, it will try to make its weight more similar to the input data. At the end, what happens is that the weight vectors for each input become like the ideal training patterns which are presented at the input. They try to look at the average vector, a kind of vector that is able to represent all the possible inputs of this kind of network. There is, of course, a problem. If there are no natural groupings in the patterns, in the input space, if there are no clusters, basically, okay, what's going to happen if you use unsupervised learning is that the weight vectors may never stabilize. They will always change as new patterns are presented at the input. So the algorithm will diverge, will not be able to converge. Another problem you might have is that the final state that the network will reach may depend on the order that the different data points were presented. So a typical example of convergence, it will look like that, like in this slide. So you start with some kind of data points. These are represented by these crosses, and you have some initial weights. And the initial weights, you know, they are randomly generated. They are away from the cluster centers. As you can see, you know, there are natural groupings in these data points. There are groups, 3 groups, as you can see. So before training, it will look like that. After training, the algorithm gradually is going to update the coordinates, the locations of this of the weights, and the weights will move close to the data points, will become more similar to the data points, becoming like cluster centers, basically. Okay. This is going to happen in when the algorithm converges. No, there is convergence in the algorithm. If there is a problem, then you may end up with situations like this one. Uh, in this case, the initial weights, you may have initial weights which are very far away from data points, and which means that some nodes may never win. So you have what we call the dead units. Okay. There are ways in the literature to sort out this kind of unpleasant situation, obviously. So for example, you can produce a more balanced type of training by adding negative bias to each node. You have techniques which make it hard for certain nodes to always win, and some other methods so that we try to produce a more balanced approach. These are techniques which have proposed in the literature. In general, to solve this kind of problems, we use, as you can see, we have learning rates. The learning rates in general neural networks is an important parameter because theoretically it's the way we have to guarantee convergence of the training procedure, of the training algorithm. It's the same kind of situation with the supervised learning. If you use a small learning rate, then you have slow training, but it's easier to guarantee that the trajectory is going to be smooth enough and you will find a good solution. In this case, the solution is the cluster center. If you have large learning rates, then it means that the cluster centers always change, and you may have problems like with oscillations, like I show you in the supervised learning example. So you may face with a similar kind of situation where the weights radically change from iteration to iteration. Okay. If you have clusters which are very close to each other, then if you present an input, that may cause the weight vector to go into move into the neighborhood of another cluster of another weight vector. Okay, so the weight vectors, as we said, represent cluster centers. It's basically like you have an input, and then one of the clusters invades in the neighborhood of the other cluster, and that will obviously disturb the whole clustering process. It is one of the problems of this kind of methods. I have here a generalized scheme which shows you the different stages of a general kind of clustering algorithm that is operating under this kind of unsupervised learning regime. So basically you have some stages, we initialize the parameters, and I have a reference which provides different details of different schemes that fall into this kind of model. As you understand, there are different supervised learning algorithms, okay? But this scheme shows you the basic characteristics that all these kind of training schemes have. So first, there is a kind of initialization. Then there is a stage where we need to define the winners. And there are different ways to do that, as I explained. And then we have we have to measure somehow similarity between inputs and weight vectors, or we use some other condition depending on how each algorithm operates. Many times we use we have a maximum number of clusters because it's possible to specify a maximum number of clusters and leave the algorithm to discover whether this number is necessary or not. Okay. So you set an upper limit to the number of clusters that you allow the algorithm to generate. Then there is a phase where there is a parameter updating. And in this case, you can see that there are two ways. There's a different formula if the node is a winner. Otherwise, there is another equation which is used. So it's not zero, like in the example I showed you before. It gives much more flexibility and it allows you to alleviate some of the problems that I mentioned before. And then it's an iterative process. It runs until convergence occurs, or you have reached the maximum number of iterations. Okay. And as I said, there are different ways that you can implement each one of these steps. How you initialize, how you determine the winners, what kind of criterion you use to measure similarity and terminate the algorithm, and how you update the parameters. So there are different ways, as I said. There are different functions that one could use to calculate the corrections. The learning rates, it's possible to use different learning rates, different for the winners, different for the losers. And that helps a lot in terms of convergence. Defining similarity is another parameter, and there are different ways to do that. We can also define a threshold of similarity and use it to compare the distance measure that we're using, compare it against the similarity threshold we have specified. And for termination criteria, we can compare the weight updates and see whether the weights are updated enough. And this is done by comparing the values of the weight vectors against some kind of threshold again. And if the changes in the weights are very small, then we use it as a termination condition. We stop the updates of the algorithm. So depending on the different choices we're going to make to the steps A, B, C, D in the previous algorithm, we can derive different kind of unsupervised learning algorithms. Okay, you can come up with different kind of algorithms, and most of the algorithms that have been proposed in the literature fall under this kind of scheme. So these are the sources I use today. We go back to Negnevinsky, which is the core text, and I have some specific chapters for you to read. And the idea of a supervised clustering, specific chapters from this book by Theodoridis Kountroubas on pattern recognition. This is the paper that introduced the globally convergent version of the RPROP algorithm, which is included in the R neural network package. And these are some references to books which are available online, specific chapters which cover the material that I presented today. Next week, I'm going to continue with neural networks and deep learning and present recurrent neural networks, dynamic neural networks, networks where we don't have only information that goes from the input to the output, but there are also feedback connections. Okay, these are very good models to represent things, sequences that change dynamically. And I have links to some online resources, 2 papers that introduced the backpropagation, versions of the backpropagation to train dynamic and recurrent networks, which are currently used in packages today to update recurrent networks. There are models, classic recurrent networks, LSTM networks, based on these kind of ideas. Okay, so that was the pre-recorded lecture. I will see you in the live session later this week. Okay, bye for now.